record. Okay. Yeah, sorry for being late. So let's get started. Once again, any question from this time? This time we go over, which one is which? Go over shorts. Yeah. This time we go over the shorts algorithm. We present shorts algorithm in another view. And anyway, this is a schematic for shorts algorithm. It's the phase estimation on this multiplication unitary, or you can think of this as a oracle. Anyway, so it's a phase estimation on this multiplication unitary where we know the eigenvalues are S over R, where R is a period. And so phase estimation of this, you start with O0, you do Hedema to a T to make it equal superposition. Then you phase kickback with this multiplication unitary, then you do QFT minus 1. And we also see this in another view. So basically, we are measuring the second register in different bases. We see that if we measure this in computational basis, then the first register becomes this impulse train state. And then we think that if we do Fourier transform impulse train, you will get another impulse train with spacing being 1 over R, and so you will get a random S over R. Okay. So that's a quick review of Shor's algorithm. And if you have no question, then as we said, we are going to spend a bit of time talking about how to use IBM cloud computing. And there are multiple ways, so maybe I'll start with here. And so their website is kind of confusing right now. They have multiple different ways, multiple ways you can do their online. Oh, excuse me. Yeah, there are multiple ways you can use the IBM online resource. But what I found out currently, the easiest one is you go IBM quantum learning. Okay, and I think you can even go with and so you will go to this page, and then the easiest one is you could just go to this composer. And I think you can even do without. Okay, so there is the first time thing, and I guess let's just close this. Yeah. Yeah, and so you go here, then you have a very intuitive GUI here. So they will start with some qubit, and so you have qubit 1, 2, 3, 4, and you have the C4 means 4 classical wire here, and then you can just do put like gates here. So you have a pretty intuitive GUI. And so you see that we have a Hedema and a C0, so we are creating like a EPR pair between those two qubits, and you have some measurement probability here, measurement probability here, and more measurement probability here, okay, etc. And so this is really intuitive. And but before we go into more detail, so this is then you can do without a count, but it's better to do this with a count. So if you want a count, then you just press sign in here, and you will go into the create IBM ID. This will enable you to do things that more technical here. So so you'll go to create IBM ID, and you fill a whole bunch of things, and you create a really long password here, and that should be free. Okay. But back to the thing we had. Okay, so if I actually go with my IBM ID, okay, can I do this? Continue login, and does it send me a verification email? No. Okay. Yeah. And so now I am signed in. Okay, and so I can continue to do this, and now I can have I think associated with each ID you have your save file. So I have a bunch of untitled circuits saved here, right? And yeah, so for example, this one is more complicated, I think, and then we have an easier one. Or okay, so maybe let's start with the newest untitled circuit here, and give it a alarm name. So then today's date, 2012, 11, 13 class. Okay. Okay, whatever, saved. Okay. And I misclick a little bit. Okay. And yeah, it's nice. Our cookie is able to save all these things. And so let's play with this a little bit first. Let's see. Oh, actually, there's something I forgot. But okay, so we have 1, 2, 3, 4 qubit. But I guess we don't need too many. Oh, okay, so if we want more qubits, then we just click on. So we left click here and then we add more or delete it. Because this delete a qubit, this add a qubit, and this will add another qubit. And but I guess the important thing to say here is this is so for now we are running on simulator. Those are like classical simulation of whatever quantum circuit you have here. And also if there is 2 qubits and the display here is ugly. Okay, so let's say we stay with 4. And okay, so right now those are classical simulation, and but it's a really small quantum circuit, so that you can just calculate very quickly. Okay, so let's go through gate one by one. So this is heteromer, and we have this is S gate, and this is C naught, and then we have Toffoli, etc. Okay, and if we want to remove, we can press delete. Okay, and okay, so heteromer C naught, heteromer X C naught, and control X, which is equal to Toffoli. Then we have swap gate. So this will swap. Maybe I'll swap those two. Then you change it to somewhere else. And this is, I believe, is identity. It probably do nothing. Okay, I'm not sure why we have an identity gate here, but we do. and the T gate, S gate, Z gate. Okay, Z gate is pretty good, and T gate is pi over 4 gate. That we talk about. So the T gate and S gate, then S is the square root of Z and the T is square root of S. Okay. And then those two are actually not Hermitian, so you also have T dagger and S dagger, etc. I forgot which one is P gate, but you can look it up on our textbook. Then we have RZ here. Okay. So RZ, then we can do different angle. Okay. So now maybe let's go into more editing of all those gates, because we have seen most of them. Okay. I guess that's okay. So you have a really weird gate down here that probably will have trouble with using 0. Or this is reset. Okay. And I guess the more important one, then we have measurement, and the measurement seems to be always in computational basis. So for measurement, you will measure it. So Z, it says measurement 0 means it is writing down the measurement result to the zeros of those 4 classical wire. So there are 4 of them. It's 0, 1, 2, 3, and we can put more measurement. It's a little dumb, so you need to put the measurement one by one. There is no major whole thing. Okay, and we have too many qubits. It's annoying. So maybe get rid of 3. So. Okay, so measure to 0, measure to 1, measure to 2. Okay, and let's talk about how to change the gate a little bit. So the dragging here is really nice, but I haven't found out any way to change the register with dragging. So I think you need to to change which wire is connected to, you need to do editing, and you just change it here. So there is a control qubit, there is target qubit. So maybe I should want to change target qubit to 2, and you will go to like this. Okay, and yeah. So in general, if you want to change any detail of your gate, you can just click on it, and it will show here. Okay, and yeah. So I think mostly is when you want to change the two target when you have multi-qubit gate. So you can swap different things. Okay. 0 and 3 and drag a little bit. And okay. Now we see this is a little annoying because it keep auto collapsing to the minimal circuit, so sometimes you need to change your order a little bit. But it's okay. And yeah, so also for this RZ, I think you can change the angle. And so it's power 2 here, so you can change power 4. But maybe this will give us trouble later. We'll see. Okay, power 2, and let's make the circuit a little more interesting. So let's put another C nut here. And say let's change the control to the target to 1. Okay, so now we're everything doing something, and maybe let's swap the Z here. Why not? Okay, and also let's put the RZ here. Okay, and okay. Now this circuit is really weird, because I'm seeing the state vector is nothing as a probability vector. Okay, why? Oh, okay. So state vector is different from the probability vector because I have a measurement here. So it's saying that I measure everything. So wait, I don't think. Okay, so I think it's because I'm saying I measure everything, so the state become O1. Okay, so if I delete those measurements, let's see, yeah, then my state vector will become more like the probability vector. So it's saying the state is 0, 0, 1 and 1, 1, 1, 1 with different phase. Okay, so here we have a little more information. So here on the state vector, you can also see the phase. Okay, you see the phase 15 pi over 8 and 15 9 pi over 8. And here you just have probability. So probability will be amplitude squared. So I guess the state vector here just have more information. But if you put the measurement here, then the probability is already measured, so it just becomes something. I think it's set to 1. So I measure everything. Then and and the measurement is also sent us. Okay. So measure everything, then you actually don't see the output result. You have some probability, but but the probability here, I guess, is still correspond to why is this such a weird probability here? Okay. But anyway, output probability across computational basis. Maybe let's try an easier example. Okay. It's stuck. Okay. Wait. Let's wait this a little bit. Okay. No, that's not a good outlook on that. Although maybe it's a Microsoft Edge being weird. Not too sure. Let's see. I guess, well, we're waiting. Any questions so far on how to use this composer? I think it's pretty intuitive. Okay, but it's stuck here, probably because I'm also streaming. And that's annoying. So I guess I do refresh this page. Okay, let's kill it. see that it's computational heavy, but let's try to go back with an easier example and try not to break it. And then I already still signing. And okay, let's delete something here. So, oh shit, deleting this just crashing it. I think I trigger enough bug here. So I cannot delete. If I click on it, it will get stuck. Okay, so we have a corrupted file here. Okay, so let's try to get something new without. Maybe I should kill a cookie. Try to create a new file to see whether we will get off this. So new file, can go new. Okay, oh, okay, we're outside this. So yeah, it's a bit tricky, but let's do an easier circuit. So let's just do this circuit we know. Let's create a build state. Okay, build state like this. And if I get Z here, then we'll get the href here. Okay, delete the Z, and let's see if we do more measurement. Does this also crash it? Okay, so we do measurement, and somehow it give me different probability. Oh, probability. Okay, so probability here is down by the same point. So the probability here since it is not exact because it actually do like 1000 rounds and see the distribution to estimate the probability. Okay. And yeah, and things like the probability will, if you do measurement, it will correspond to the classical probability here, and then but if you do measurement, then you just say there is no state vector. Okay, so if you just kind of want to see the vector, then you don't need the measurement. And but when do we need measurement is if we want this probability on actual quantum computer. Okay, so let's go to actual quantum computer is, okay, so let's say it's called Bell. Okay, and then we start up and run. Okay. And you just click here, then you will see you have a whole bunch of IBM computer to choose from. Oh, why is it so good today? Okay, and yeah, so that will list the online IBM quantum computer here for you to choose to run your job. And okay, so you have a whole bunch of parameter here, and here I think, okay, so it says. This is the number of qubits, and this is error per layer gate. So this is basic error rate, and what's this? C plus H. Measuring hardware. Okay, so this is like the speed, I think. And anyway, and but you see that this big 127 qubit one is very popular. You need to really wait a long line. There are 2,000 jobs pending over the world, and this one is also popular. So let's go to what's this one? Okay, so this is a simulator. So this one is actually a simulator, and they say they can simulate up to 5,000 qubit, but it was similar to this thing we already have. So let's not run a simulator. But wait, oh, but today's okay. But today we only have a simulator online and a big one. Okay. No, that's annoying. Okay. So today they took all the small quantum computer type system. Okay. That's why we have 2,000 jobs here. But so we probably will not be able to finish waiting in line today. see detail. Okay, but when you are more lucky, then you will have a smaller quantum computer here. I'm not sure why they only have the big one with a lot of job here, but okay. Okay, and anyway, let's try to wait in line, and we'll see. We'll need to wait a very long time. But we try to wait in line, and we can see how it is going. And so we can probably go teach you about other things and then come back. Okay. So yeah, it is quit here. It will say in this tab, it says the job is getting quit here. Yeah. And so maybe I can try to Google something. IBM quantum computer status. They just taking down today is lower than usual. Do they have? Okay, maybe let's try to find out later. Okay, and yeah, this job is waiting, and I'm not sure when are we going to get a quiz through, but when you quiz through, then you will you will produce something similar to this and get us a result. And then maybe let us cheat a little bit, so let's get rid of running on actual quantum computer, and we run online simulator. Okay, and the simulator should be similar to this one, but maybe it's a little more powerful. Okay, and if we do simulator, then we'll see. Then the simulator is running on it, and it says the result. Okay, so result is will be this form, and it just say there is some distribution on what's the measurement outcome here. Okay, so it's going to correspond to this measurement outcome. But okay, yeah. And the measurement outcome is 4 bits because we put the 4 classical bits here. Yeah. And not totally 50-50 because it's a simulation and run with 1024 runs. So we just run the circuit 1000 times and see which is the amount of measurement being 0, 0 you get, the amount of measurement 1, 1 you get. And it's a run simulator, so there is no error, you get the other outcome. Okay. Okay, and so that's about it. So this is the basics of using the composer, and but now we only have GUI, and if you want to be more like a computer science people, then we have quantum code here. Okay. And yeah, so this is real time, and you can just do. You see that if you add things here, and they will change the code here. And actually, you can also edit the qubit by just changing the code here. So delete this line, I believe they will corresponding to changing the code, changing the graph here. So you can also just change things on the code here. So say this Control X, you will say like from 0 to 1, and then you can just change it to 1 to 0 like this. Okay, and yeah, and your state will change. And maybe I don't want measurement, so let's delete the measurement. Okay, delete the measurement. Okay, and yeah, so you will have very easy code here, and code here you can actually do something a little more powerful. You can group things together, and there is this group function. Okay, and you can call this whatever. It's not really bell, so maybe ball. Okay, and yeah, so you see that is you are able to do this group of gates, so you can create something like an oracle, like this. and auto create this this block of code here. That's kind of create a function, and then you also create this bold GUI here, and maybe let's rename this to Oracle. Oracle. Doesn't change. Let's see, can I rename this thing? Rename Oracle. Okay, the name here and then there doesn't seem to sync. But okay, yeah, you can rename this, and yeah, and then you can put. Can I? Oh, I think I crashed it again. Annoying. Okay, so that's this is dangerous function to do. Delete. Okay. Let's put easy thing back and try to do this again. See where it crashes again. So group. Okay, wait. Let's delete this. Click on group. Okay. So let's circle those two things, and that's on group, and this is a group. And let's call this Oracle to see if. Okay, I should not call it or. So let's delete this once again. Okay, try one more time. Group Oracle table. Okay. Okay. And hopefully now it's okay. Okay. Then now I can paste more Oracle like this. Kind of like an Oracle program. And down here we'll do this as like a function. And then I think I can even do like a 120. How does it say? Okay. Or you just say BA. Yeah. Okay. And let's try to remove them without breaking it. And maybe ungroup. Okay. And remove this here, and it will remove there. Okay. Yeah. So that's one more thing you can do with this composer, and and it's nice because you can play it with this GUI. And but if you want to get more technical, then you can do this open. Oh wait, so maybe that's finish this part. Okay, so you have some kind of pseudocode here, and you can also import and output code. So say you can export code, and then, yeah. Then it has this weird file extension QASM, and you save it somewhere. And then later on you can import it. Okay. But I believe also all your code you can just save here, and is linked with your account. And then finally, to go to more technical way to deal with this is you can click on this go to Quantum Lab. Okay. And then you will go to this IBM Quantum Lab service. That is more rigorous, but why is it getting stuck here again? Okay, I guess it takes some time. Quantum Lab. Okay, yeah. So now we are going to actual more like a programming. So we imported the we imported the composer file we just have, so you can see that. And now this is like in Python language. Okay, so now this is, I guess, more rigorous or more formal way to do the quantum circuit is you can write in this Python language, and I believe this is called the Q-ski language. And so here, so we were being in a composer type, and now we are in a lab type, and lab type, you can write things in this kind of notebook, and yeah, so you can see the language is like Python. So here, because we import from the composer, you already input something required for us. So a lot of important things are already imported, and yeah, and you see like most of the content thing is from this Qskit package, and so you can see here some of the basic Python code, Qskit Python code. So you have this create some quantum register. So here we create 2 quantum register, then we create 4 classical register, and we say our circuit has those quantum register and those classical register, and then then you here we say so circuit.h is a function that adding a headema to your circuit. So you are adding a headema on the 0th qubit. Then here we are adding a control. So Cx is control x. So we are adding a control x from qubit 1 to qubit 0. Okay. And so this is a Python code, and I think we can do run. And here it's a bit funny. Then we can say editor is composer. So if you run this code, it will do like a composer like thing here. So actually the Python here also, you can also do composer. But if you add more things here, I think it doesn't actually. Okay, so this is a partial composer. I'm not sure what you think here it will be. Oh, if you think here, then it will actually create another thing that's whatever the composer result you have here. Okay, so that's kind of nice. But from here, then you want to send a job onto the actual cloud computing, then it will be harder. Then you need to look up in more detail, in more detailed documentation of the Qski code, and yeah, so you need to look up what the IBM quantum computer is online. They look up their code and try to put the Python command here to actually run on the online version. But I think on here, then you can run on, there are commands that let you run on simulator, kind of like the composer simulator we'll be doing. So can I do this double tap thing? Okay. Yeah, so here we have some of the simulator result, and you can get similar thing on this Python console here. But Python console, well, there are a lot of different commands that do different visualization. But I think the composer visualization here is actually just better than what you can do in just one of the basic you can do from the Python code. Okay. But Python code, obviously, you have all the Python things, so you can do more programming here, like you can run for loop, etc. And I think it's a bit hard to run loops in this composer. Okay. So this Python thing is more powerful, and here is a way to compose your Python code on the IBM cloud, but also you can just download a local version and and maybe run simulator locally, and when you want to run on their cloud computing upload, and what you do is you want to Google Qskit and try to install it locally, but there are more installation, and I think we are out of time, so we'll not say it. And yeah, so I think if you want to install, then you click learn more, and but I forgot. I think it's in install and set up Qskit. Yeah. Mm, yeah. So basically, you need to set up the Jupyter environment on your computer, and then you can run local thing, kind of like this console. Okay. And anyway, so that's a lot of demonstration about uh, IBM cloud computing, IBM cloud quantum computing. But I think for our homework, we will just require you to run the easier one, so you can just try to run on their composer, and yeah, and we'll have some easy project for you to write the composer quantum algorithm here, and you can upload your code, and so we will see your code is correct, and maybe we'll also let you run simulation, run actual quantum computer, and you can take a screenshot of your running result. But hopefully next week is not all like this. Okay. And yeah, so right now it's basically I took almost everything down. So it's very annoying. Is it because, yeah, I think they are just down. Let's see. If I go to here, does it make it better? Doesn't think so. And if I do this, will it tell me what? Okay, computing resource. So this is the computer we're queuing for. It has 127 qubit, and it connect like this. And some of the qubit are bad, so it has a different color. Yeah, so it is error rate. So the lighter color, the more error it has. And okay, so here what do we have? So computing results here. We have those things just listed like before. And the old system, why do we have a whole bunch of 127 systems? But okay. So we also have a few 27 qubit systems online here, but they are not providing those to free users. Yeah, they're locked. Well, but okay. A few days ago, they still have the small one, like 5 qubit one, but seems like they are taking those down. Not sure whether it will be online, and so if next week they are all online, then you can just turn in your homework with is only simulator, I guess, because it's pretty hard to get in line with those big computers. But I guess if you submit early, you can also just wait in line for a long time. This will probably take, I'm not sure, a few hours. Oh, this one. Oh, we're almost here. It says in 6 hours, but we already quit for like 900 in less than 1 hour. We're in position 34, so maybe next class we'll already see the result here. You just need to quit for 2 hours. Okay. Yeah. So that's that. And I think that's all I want to say with IBM learning. And yeah, if you want to write something more serious, then you are welcome to learn Qiskit. But we are just having a quick idea, like when hand on quantum circuit, then you can run this composer. But as we see, the composer is prone to getting stuck here. So, and yeah. So another thing that I get stuck is I've tried. So they have weird thing. So I think the RZ is a little dangerous, and also they have a weird option of like do control RZ, but yeah, classical control RZ, and I think if you put this on your quantum computer, then it will also be made on you. So The simulator can do this, but I think some of the get you run on the cloud computer, then they are not happy. So wait, so let's actually try. So condition, I guess you only condition on classical thing, but it's weird. 0, 0, does it make sense? 1, 0, less than 4, so I need to be 1, 2, 3, 4. Equal to 2. Okay, so it's classical control on some value. Okay. But the cloud probably cannot do this. Okay. And yeah, so I think that's it. And we're actually almost spend 1 hour on this. So I guess we can, if we don't have questions, then we can take a break early and let's start in 10 minutes, and then let's go back to our theoretical discussion on global algorithm. Okay? Okay, let's take a break.边先audio 啊，算了，还是不要改好了。 got stuck again. Why did this go big? Freedom alignment 哦，所以其实可以乱放。哦，这样子就不会被压扁了。Freedom 真好，这样好像比较方便了。为什么不给我放这个东西？哦，原来只有2个 Q 边。哦，我又卡住了。Freedom alignment 看起来不太行。可以耶。 everyone back? I think most of the people are back. And yeah, so I think it's about 5 minutes, so we can back to our class. Yeah. And yeah, so now let's go back to our theoretical discussion. And so continue the story of theoretical discussion. So we finished teaching about Grover's algorithm. And now I want to teach another quantum algorithm, that's Grover's algorithm. So those is second of the two most famous quantum algorithms. So first one is Grover's algorithm because it can solve factoring, and then that means it can break the RSA-based crypto system. And then the second one is Grover's algorithm. And what does Grover's algorithm do? It does a search problem. And it's very different from Shor's algorithm. So Shor's algorithm is like a exponential speed up, although the exponential speed up is not theoretical because we don't know how fast the classical algorithm can do. But we think it has an exponential speed up, and it's very practical because it solves a very concrete problem. It solves this factoring problem, and you can use it to break crypto system. And but Grover's algorithm, well, first of all, it doesn't have exponential speed up. It has a quadratic speed up. Okay. And so what problem it solves? Well, it also solves a very practical problem. It solves the search problem. So it says that if you have n items and you want to find a special item out of it, then the search problem, you only take a square root n time. Okay. And classically, you can really easily see that this problem takes the order n time. So this search problem, so what is this? Okay, so example kind of bad is if you try to break NP-complete problem brute forcefully, right? So you try password. Okay, so maybe I'll say this. So the example is kind of like sorry, I forgot to connect this. Yeah. Okay, try password is a little weird because it's interactive. And let's say one-time function. Okay, so maybe let's still say example is you try to where am I? So this is here, and okay, it's here. Yeah. So example is you try all witness of NP problem. Okay. So we know that the NP problem you can, if it's yes, then it has some witness that will get accepted. And a stupid way to solve the NP problem is you try all witness. Okay. And so you try all witness in classical, then it's about 2 to the n tries because there are exponential number of witness to try. But if you try all witness with Grover search, then you only need the square root of 2 to the n. So it's like this. Okay. And okay, so but it's very different from Shor's algorithm because it don't have an exponential speed up. So it's only a quadratic speed up. And this is something that this algorithm get complained about now and then because, well, it's not such a big speed up, and right now the quantum computer hardware is not so good. So maybe even with a quadratic speed up, running algorithm on quantum computer might be still slower than a classical running on classical computer. Okay, and so that's kind of a bad part. But the good part is that this algorithm is theoretically very clean. Okay, so this is the Oracle algorithm, and you can actually give Oracle lower bound. I guess the Shor's algorithm also have a kind of Oracle lower bound, but that's okay. Yeah, but but let's not go into detail about the Oracle version of Shor's algorithm. But anyway, on the Grover's algorithm part, it has a very clean Oracle lower bound. So we are able to show that oracle lower bound implies the time lower bound. So we can show that the Grover's algorithm is actually give you exact quadratic speed up. Okay? And this kind of theoretical analysis generalized to a lot of different things. Okay? And yeah, so this is an example where quantum query complexity is very useful because we see that its quantum query complexity will be equal to its time complexity. Well, I guess is equal is up to some constant like we already say in computer science. Okay? Yeah, so equal up to like a big O or big theta. Okay. And yeah, but it's a theoretical claim. And also, good thing about this is that this is solved a very simple problem, right? The search problem. You can think like all kind of algorithm you will do kind of brute force search, and say like you can try the weakness of a p-complete problem, and maybe you try to invert the one time function. So maybe you try to invert one-way function, you will try all the pre-image, etc. And yeah, so whenever you have some kind of brute force do thing you do in your algorithm, then you can try to replace that with the Grover's algorithm. So Grover's algorithm can be applied to a lot of different settings and give you some up to quadratic speed up. And yeah, so that's also something that's good for theoretical. So you can design a lot of quantum algorithms that has those quadratic or polynomial speed up just based on this Grover search. Okay, so that's background about Grover search, and now let's go into the mathematical detail. And well, as we say, this algorithm is a lot about quantum complexity or oracle complexity. So that's a review about those quantum oracles. So we've been talking about this before, but we didn't use them in Schwartz algorithm. So let's have a review. So remember, the oracle is like a black box OF, and it stores information about some function. Okay, and here this is a little confusing because they are kind of two functions. So we kind of think OF encodes things about this function, or we also think the truth table of this function is a big and big string. Okay, and yeah. But anyway, about this function, so if we write this in this function way, then we say OF tilde some x and q, then is so x is the input to this function, so there are two inputs. It's very confusing, but so we can think about there is this input to this function, and so we'll compute f of x, and you just write it on this record register, and so this is O plus here. And for now, that's restricted is f to binary, so this O plus here is unambiguous. Okay, so O plus here is just bitwise XOR, and f is a binary function, so from some n bit to 1 bit. So this f of x is 1 bit. Okay, and as we said, there are kind of two inputs here. Okay, so there is an input x here to your function f. Okay, and you can also think about your f. So the truth table of your f is the input to our HO algorithm, to our oracle algorithm. So our oracle algorithm will take a whole bunch of these O tilde alpha, put a whole bunch of those black box in your circuit, and try to solve something about f. So remember, like in Dirichlet's algorithm, when we want to say, so there are four possible f, we will say f, so Dirichlet algorithm, right? And we have f, it has four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1 is 1 bit f. And we want to say, are they balanced, or are they balanced, or they are this oh sorry, this is balanced and this is constant. Okay, constant or balanced. Okay, so yeah, so there are two inputs, and but I guess we can also kind of get rid of this f description, and we just think about this truth table of f. And so if f is a small n bit, is truth table f big n bit, and so we kind of just think this big n bit as a big string, and then this x here is something from this x here is a small n bit string, and it's something from 0 to big N minus 1. Okay. And so this x is like an indexing to this truth table of f. Okay. So we are thinking we can also kind of forget small f and just say this f sub x is now like this. So we can kind of think f of x as like f sub x. So it's like the x bit. So the x bit of this big and bit string. Okay. Of f string. Okay. Of this of truth table. So can kind of the x bit of the truth table of small f. Okay. Hopefully it's not too confusing. And anyway, no, but I guess we are still stuck with this small f in our notation. But and now back to search problem. What do we want search problem? In search problem, we want to find. Okay, so this is a 0, 1 bit string. So maybe 0, 0, 0, 1, 0, 0, 0, 0, 0. And what we want to do is we want to find some 1 in this string. Okay. Yeah. And when there is some position that have fx equal to 1, then we say it's a mark item. Okay. So f of x1 equal to a mark item, so I guess this actually say x is, then x is a mark item. Okay. So if f x is equal to 1, then x is a mark item. Okay. So we want to find this x. And so if there is only one of them, you want to find it. If there are multiple of them, then it's a bit weirder. But right now, let's say we just want, if there are multiple of them, we just want to find one of the multiple. Okay. So that's a search problem. Want to search something with f of x equal 1. And I guess back to our NP complete example. So maybe this f is checking whether your witness is actually a witness to your NP problem. And so we want to search for some witness x that will pass your NP verification. Okay. And yeah, now back to the quantum query complexity. Okay, so quantum query algorithm, we have this mental picture. So quantum query algorithm is a circuit that has many qubits, and it will put those oracle inside, and so this oracle will tell you information about this f, and then between those oracle you can do whatever thing that you do that doesn't depend on f. So you have arbitrary inventory that ignore everything, and so it's this layer algorithm. And at the result, and at the end, you want to learn something about f. Okay, so learn something about f. Okay, learn something about this small f. And for the search problem, then you want to, this is exactly the one thing you want to find. So we want to find the x such that f of x equal to 1. And I guess if f is an O0 string, then you want to answer that there is no such x. Okay. And yeah, so learn something about f and back again. So in the George's algorithm example, they want to learn f is constant or balanced. Okay. And yeah. And then the query complexity is how many of those OF tilde you put inside. And you want to minimize the number of tilde you use, because we think that will also relate to the time complexity of the algorithm. Okay, and so that's OF tilde, and you might be wondering why we put tilde here, because there is a better OF we want to use. Okay, so we actually want to use the face version of the quantum oracle, and this is done in homework, so hopefully you are all very familiar with this. And so the idea is that you can do phase kickback on your quantum algorithm. So it's of tilde x. If you put the record register as a -1, then you see that when f of x is 0, then obviously nothing happens. And f of x equal to 1, then actually this minus state still stays a minus state. So if x equal 1, then you add 1 on the second register, so 0 becomes 1, 1 becomes 0. So instead of 0 minus 1, you have 1 minus 0, and so this is 0 minus 1 with a minus sign. Okay. And so everything together, you see that you put a second register as a minus sign, then you actually get this minus 1 to the f of x times x. Okay. And yeah. So we can do phase skipping on our quantum oracle, and so instead of O of tilde, which is kind of writing the recording computational basis, so f tilde, once again, look at this, it's very nice. You just write the f of x in the second register, so it's like what a classical oracle will do in superposition. I guess a classical reversible oracle. Okay. But then over tilde is a very constant thing. You just write the result as a phase here. So minus 1 to the f of x. Okay. And okay. And so we have over tilde, then we can do OF. And then we'll discuss our global algorithm in terms of OF. Okay. So yeah. So for now, so later on we will use OF, and OF is this thing. Minus 1 to the f of x, x. Okay, and as we said, this is a really content thing. Okay, yeah, and a reminder about the homework. So you change O of tilde to O of here, you actually lose some information. Okay, so you can change O of tilde to O f, and it's not possible to actually change O of back to O of tilde, and then you can think about why. But in a homework, what we actually change into is control of OF. So you want to do OF on some xy, and then you go to minus 1 to the f of x, but you also times y. So it means that if y is 0, then you never apply this phase, and you apply this phase only when y equal to 1. Okay. But yeah, but we will never actually need to use this control register for our OF. So yeah. So to make the notation easier, let's just use OF for the following discussion. Okay. Because although this lose some information about f of x, it's already enough for us to do our search problem. Okay. Although yeah, it's a bit weird, but okay. Yeah. Okay. And no question. Okay. Now let's actually go to the search problem. I guess we have said most about it, but let's have a more formal discussion, more formal description. So we have f of x as input, and it has this truth table, so 0, 1 to minus 1, or possible input to 0, 1. Okay. So this is all possible small and big string, and total and possible small and big string. And the problem is you want to find some x, such that f of x is 1, and this x is called a mark item. So x is some number between the 0 and the minus 1. Okay. And also, if x does not exist, we want to say f of x is 0 for all x. We want to say it's possible. Okay. So this is the most standard. This is a search version of the search problem. And but when we talk about complexity class, lots of time we want to say decision version, right? If you still remember the language discussion, etc., want to say something in language or something not in language, etc. And so sometimes we also like a decision version of the problem where you have some input f of x and just we answer some yes or no. That's kind of like in Dirichlet's algorithm. Okay, and so we can also define decision version of a search problem. And that is just you output 1 if there is a mark item, and if output 0 if it's all 0. Okay. And yeah, so if you have a uniform x, then it's very easy because almost every x is output 1. Okay. So out of all possible f of x, then the only possible f of x that give you 0 answer on decision is every one of them is 0. Okay. But yeah. Why we want to talk about decision version is because, okay, so we can think about a relationship between those two problems. Okay, so they are basically equivalent. So well, the first thing very easy to show is that easy to see is decision version is easier than the search version. Right? Because if you can answer this problem, then you already answer a decision problem. So if there is a sum of x, then you already found it, and if not, then you will say there is not. Okay. So if we can solve the search version, then you can solve the decision version. And actually, it's easy to see that they are about equal. Because if you can solve the decision version, you can kind of do binary search to solve the search version. Okay, but that's not important here. For now, what's important here for now is the decision version is easier, and later on we'll do a lower bound on decision version. And because the decision version is easier, so kind of we'll think about honey scale, right? And then we have the search version and the decision version. And we think decision version is harder than some lower bound, and the search version is even harder. So the search version will require even more quantum query complexity. So we'll do the lower bound on the decision version. That's why we have it here. But for now, we are doing upper bound. We are going to give you a constructive algorithm that's over a problem. So actually, decision version is not too important here right now. And okay, so now let's go back to more complexity. So classical query complexity, what's the classical query complexity to solve this? Well, this is really unstructured. You can have a 1 anywhere, right? So like the hard case is actually between all 0 string, or there is a 1 somewhere in this string, and they really don't know where is this 1. So the classical query complexity, randomized or not, you need to take about order n queries. Order big N queries. So you need to look through a lot of things to see where there is a 1 inside this string. Okay, and so obviously there's an upper bound of order n where you just look through everything, and it's easy to argue that you also need the omega and lower bound to check everything too. So you need to check like a lot of constant frequency to get a constant probability of success. Okay, and that's a classical query complexity, and we are going to show a quantum algorithm that we are a little short on time, but we have when we start. Okay, we have 30 minutes. Okay, it should be enough. Okay, and then we are going to show the quantum query complexity is order square root n. Okay, and before we do that, we actually make the and okay, so this is a bit confusing. So actually, we should switch the order here, because we are talking is a bit more general. Okay, and but actually there is another parameter here that is this m. Okay, and that is how many number of mark items you have in your algorithm. And for now let's assume this m is also known to the algorithm. Okay, so you are promised that the algorithm know the number of mark items. Okay, and let's start with this. It's easier. So this is the tricky part. And if you know n, then classical you only need n over n, because if there are more mark items, then you only need to check less number of things to hit a mark item. Okay, so n is the number of mark item in this in your input f of x. Okay, and your input is small f. And okay, so that's notation. We'll see soonish to see why it's important. Hopefully you can cover it today. And then let's write down the quantum algorithm. So the quantum algorithm look like this. Okay. So you start with the O0 state as the query algorithm usually do, and then you do header map to the n, just like all the quantum algorithm we do. And so you get the equal superposition of everything here. And this state is actually important here, so we call this psi here. So this psi is the equal superposition of all state. Okay, and and here we have a small number of qubits. So this psi is like a 0 equal superposition between 0 to -1, bigger -1. Okay, and we repeat something we call Grover iteration here. Okay, so and we'll repeat it some number of times. The number of times is about order square root n over m. Okay, so I guess let's keep over m here because we already have m up there. Okay, yeah, but the exact number we will determine later. And then we do measurement, and the result will give us the mark item. Okay, so what is spatial global algorithm? It's basically two reflection. Okay, and so it contains the oracle OF. So this is the phase version of the oracle we could talk about. So that's a reminder: OF of x equal to -1 f of x. And okay, so this is a global iteration or a global operator. First thing you do is you apply the oracle, and then you do these three weird things. And before looking into detail, let's say the total result. The total result will be this gate: 2 side, 2 times projector on side and minus identity. And this is actually a reflection around side. This is a very geometrical representation. We'll see later. Okay. So you just keep doing those two things, so OF and the reflection around side, OF reflection around side. And if you do a good number of times, then measure and you will get a mark item. Okay. And here, the convention on notation here is a little weird, but we follow the book. So those 4 steps together, so basically those 2 reflections together, we call it a global iteration or global operator. But I think sometimes also people also call just those 3 parts the global operator because it's the oracle part plus some like a global algorithm part. But yeah, but that's try not to do that here. So we follow the book notation and we say those 4 things together is the global iteration global operator. Okay. So that's the high-level overview of what this algorithm do. Okay. I guess we don't need to go into detail here. Okay. And then, okay. So what does this actually do? We say we apply OF and we apply this twice projection on side minus identity. And what will this do is 2 reflection on some 2-dimensional subspace, and we'll kind of rotate our quantum state from this side to the mark state. Okay. And I guess okay. Okay, so let's explain why these 2 side minus identity first. Although we can, I think if we want to be really quick, then we can also just say, first apply this and then we apply this. And because in our oracle, remember in our oracle algorithm, we say our algorithm is we apply unitary, whatever unitary, and so this unitary one requirement doesn't depend on your oracle. And then we apply our oracle. You apply whatever unitary and you apply oracle. And now you see that this thing already satisfies the condition being arbitrary unitary that doesn't depend on oracle, right? Because there is nothing dependent on f here. This psi is just this totally mixed, not totally mixed, sorry, the uniform superposition here. So this is a reflection around uniform superposition, although you will see later why we call it a reflection. Okay. But anyway, here we want to do it in, I guess, a more basic gate. So we are writing this as something that more obvious about how you create this gate out of basic gate. Okay. So we break this into 3 steps. So first is you apply the head module n, just this head module n once again, and then you do control phase shift. So it's kind of like this oracle thing. But anyway, so it says that on some computational basis, state x, then you go to minus times -1 to the delta x0. And this is 0 is O0 state. Okay. So here the x is in computational basis, is a comp basis state. So x is in 0, 1, 2 to -1. Okay. And yeah, and so what does it say? So the delta x0 says that you apply this -1 only when x equal to this 0. Okay. And otherwise you don't do this -1. Okay. And so that's what it means. Okay. So only on 0 you get an extra phase of -1. Okay. And that actually means a phase of +1 because you only also have a -1 phase here. So all of those computational base state, 0 will get no phase, and 1, 2, and -1 will get an extra phase, or will get a phase of -1 from this -1. Okay, so you do this thing, and then you apply Hedema to n again. Okay, so that's what those 3 steps do. And yeah. And here we have some discussion on why these are easy to do. So Hedema to n, so Hedema is usually one of your universal case set, so it's easy to do. And so how you do this -1? Okay, so how you do this -1 to the delta x0? So first you can just apply some global phase -1 in some way, and then this delta x0 is multi-control phase gate. So basically you want to control so remember the x being 0 is 0 to n. Okay, so this is basically yeah. So you control every bit being 0, then you apply z gate. You can apply the negative of z gate. Okay. Yeah. So you kind of yeah. So anyway, this is like a multi-control z gate with some extra phase, and you can and we've been talking about multi-control. Yeah, so it's a multi-control of this negation of z gate. So you control on the n-1 bit being all 0, and then on this bit you apply this gate, and that will be this delta x0 -1 to the delta x0. Okay, so that's some wavy explanation to try to say why this is possible from basic gate, because in long time ago we say every multi-control gate we can control from our standard gate set. Okay, and anyway, let's back to Gobel algorithm, and so what are all those 3 combined together? Okay, so let's see what is gate 3 first. Okay, so this is a reflection, and we will talk about a lot of reflection. So step 3 is the first reflection we see, and it's a reflection because well, reflection are gates look like this. Okay, so it's twice the projection on 0 minus identity. Yeah, so it's this gate. So this gate on every computational basis state, and then the computational basis is basis. So step 3 just apply this gate. 2 times the projection on 0 minus identity. Okay, and so what is this reflection about 0? Okay, so first see step 3 is actually this thing, and this coincides with our analysis on what step 3 do, because if you put x as 0 inside here, then you have this twice projection on 0 give you 2 times the 0 ket, and minus identity on 0 give you 1 0 ket, and so it's twice 0 ket minus 1 0 ket, so it give you 1 0 ket. And then if you have other computational base state, then its inner product with 0 is 0. Then you just have a minus the x ket, so minus x ket. Okay, so you do 0 to 0 and x to minus x. And so what happens is, say you have whatever. So it's a bigger dimensional space, but let's think about maybe I'll draw this in like a 3-dimensional, right? So if you have this 3-dimension of 0 and some x1 and some x2 here, and then you think about you have some vector here, right? And then you can write this as a component on 0 and the component on x1. and the component are x1 and x2, and then you apply the twice 0, 0 minus identity. What happens is this 0 component will stay fixed, but this x1, x2 linear combination component get minus sign, so you get this vector. Okay, so you get this vector. So it's a reflection around this 0 axis, and I can only draw 3-dimensional, but you can think about this is a n-dimensional reflection around this 0 axis, because the 0 component keep it fixed, and all other component get a minus sign. And that's why I get like this. So twice of some projector minus identity, we call it reflection. Okay, so it's a reflection around this projected component. Okay, and now more thing about reflection. So step 3 is reflection, but step 3, 2, 3, 4 together is also a reflection. It's just a reflection around different vector. Okay, it will be a reflection around psi. And psi once again is gamma to n on 0, and it's a uniform superposition of all computational base state. And why this is true is you can just check this formula. Okay, so step 2, 3, 4 together is you apply gamma to n and your reflection and gamma to n. Okay, and then this is then by linearity, this thing is, so you can sandwich gamma to n on those 2, 0, 0. And then you can sandwich gamma to n identity, but so gamma to n times identity times gamma to n obviously is just gamma to n times gamma to n. Okay. And but what about gamma to n on this projection on 0, 0? Then it's gamma to n times 0 and ket and 0 broad times gamma to n. But we already know gamma to n times 0 ket is our psi. Okay. And the other way is just you flip this around. Okay. So this is actually psi broad, psi ket. Sorry, psi ket, psi broad, and this is projection on 0, and the other thing is gamma to n square, and about gamma square equal to identity. So this is identity to n square, identity to n, which we just call identity, and yeah. So the two things together is reflection around your psi state. Okay. And yeah, once again, it requires no oracle calls to OF, and also they can be implemented efficiently. Okay, so the efficiently part is the part where, okay, so we also want to talk about time complexity. So this is about time complexity, and this is why we want to write in this way. And in this way, you can kind of easily verify that those things only need the order n gate to implement. So obviously gamma to n only require order n gate, and this like order n control gate also only need order n gate to implement. Okay. Okay. So they require no oracle code, so they don't give you us any cost on query complexity, and they also when we want to think about time complexity, they don't cost too much. They are in order small n. And remember, our algorithm is in order big N, and so this is like a log order. And our algorithm is like order square root n, and so n is log n, and so this is really cheap. Okay. Okay, and now finally back to our algorithm. So what does our algorithm do? Our algorithm do. Oh, okay. So we apply OF, then we apply this reflection around psi. Okay. Okay. And now we go to more geometry because we'll keep talking about reflection. Okay. So okay. So geometry. How do we analyze the geometry? The base. First we say we have n mark item, and then we define this state. That's the superposition of all mark items. So suppose there are n mark items, then we adding together every mark item. Every computational basis there, that's a mark item. So x such that f of x equal 1, and then we need to normalize it, so you divide by 1 over square root n. Okay, and then we just call this beta. So this is equal superposition of all mark items. Okay. And then we are going to consider this 2D dimensional space. So this is the most important thing here to analyze this algorithm. Is you fix our view into this 2D dimensional space. And so remember we were in n-dimensional space. Okay, so this simplifies things a lot. We were in a bigger n-dimensional space, but actually we don't need that. We only need a 2-dimension. That's a 2-dimension spanned by those 2 vectors. That's not actually orthogonal. So one of them is the beta we just defined, and then another one is this side. Hopefully that you probably guess. Okay, so it's this side that we'll be talking about. That's the side that we reflect around. Okay, so yeah. So we only consider what these things happen in this 2-dimensional space. Space spans like beta and psi. Okay, and now orthogonal, so we can define the alpha, that's the orthogonal vector inside this 2-dimensional space. That's the vector that's orthogonal to beta in this 2-dimensional space. Okay. And so if you do some computation, it's easy to see that because the psi is the equal superposition of everything, and the beta is the equal superposition of everything marked, and the alpha will actually be everything that's the equal superposition of everything unmarked. Okay, so definition of alpha is a component that's orthogonal to beta, and it's actually a superposition of everything unmarked. Okay, makes sense. Then okay, and then what will happen is that so our global iteration only do 2 things: OF and this 2 psi minus I. Okay, and what happens is that they don't make anything. We'll start our algorithm in this psi state, so it's already inside this 2-dimensional space, and we keep applying those 2 gates. And actually, they don't get anything outside of this 2-dimensional space. So if you start everything inside this 2-dimensional space and then apply those 2 gates, they will stay inside this 2-dimensional space. So our algorithm will just keep doing things inside this 2-dimensional space. So we only need to see where our algorithm goes. Okay. And actually, there are 2 reflections, and there will become rotation. So our algorithm will just rotate this side around this 2-dimensional space, and when it hit beta, then we are lucky. Okay. And yeah, so let's go back to see the reflections. So what is OF? OF is so remember, yeah. So let's write this once again. OF on x give you -1 to the f of x. Okay. And so what will OF do on beta? Well, beta is a superposition that's everything marked. So OF on beta will give you -psi. Okay? Because beta is everything marked. And what is OF on alpha? Well, alpha is everything unmarked. So alpha is everything with f of x equals 0. So OF on alpha will do nothing. Okay? So you see that this is analysis that we do kind of similar before. So we see that OF on this 2-dimensional space is actually a reflection around alpha. Because you see you will have an arbitrary vector, then it has an alpha component, a beta component. And the beta component gets a minus sign, alpha component stay the same, so you get to here. Okay. So OF is a reflection of alpha on this 2-dimensional space. And what is the 2 psi minus identity? Well, it's a reflection on that side, and on the 2-dimensional space is still a reflection around side, because obviously the side components stay the same. And then you can think about the component that's perpendicular to side, so you have side perp here, and this component will get a minus sign because every component other that's perpendicular to side get a minus sign. Okay, and yeah, so it will be reflection around side just like our 3-dimensional case. And okay, so what will happen is that we keep alternating between this reflection around alpha and the reflection around psi, and that's called the angle between psi and alpha theta over 2. And what happens is every quarter iteration you will rotate, you will do this rotation on your side with extra angle theta. So you'll get theta, 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 and if you have enough theta, you will get close to beta. Okay. And theta here is about order square root n over n. We'll see later. Okay. And yeah, so after K go over iteration will go to the angle that's K plus 1/2 theta. Okay. So this is K plus 1/2 theta. So 1/2 you already have, and each go over iteration you get extra theta. So you go to K plus 1/2 theta, so it's cosine K plus 1/2 theta alpha and sine K plus theta beta. Okay. And so now we can answer when do we want to the algorithm to stop, because remember, so this is something we didn't say clearly, so we just say you need about order square root n over n iteration to stop. And so when we want to stop is when your state vector, so your system rotate to something around beta. Yeah. So that means your theta about pi over 2. So you do enough k when your theta is about pi over 2, then you do computational basis measurement, and with high probability you will get something. Because you are close to beta, so you measure beta, and you measure beta, you get some state that's marked. Okay. And yeah, and as we say, theta is about square root n over n, and so I should not say theta, so I should say when k plus 1/2 theta. Okay, is about pi over 2. Okay. And yeah, so theta is about square root n over n, and so k is about square root n over n. Okay. Okay. So here we'll have k about square root n over n. Okay. So that's the idea. Gk is like here, and you have k plus 1 theta. And yeah, so the proof here is really short. Okay. So proof here we just show two reflections is actually the rotation about theta. So yeah, so we have a starting. We start the work from this arbitrary. So let's say we have an arbitrary state phi here. Okay. So we have arbitrary phi as a starting state, and then we see what happens when we do two reflection. Okay. So this is just a very easy geometry calculation. So let's say the angle between phi and alpha is gamma. Okay. And so when you do the first rotation, you will get the angle gamma here. And so you reflect around alpha, so this angle is alpha, then you get another angle alpha here. Okay. This is just a reflection. Okay, so then this state is OF of psi. And then you do reflection around phi here. And then we get this G of, reflection around psi here, and then you will get a G of phi. So you want to go from here to here. And you want to know the angle we progress. So this angle x here. So you want to know how far away is G phi and phi. And yes, then you just do this middle school math. So it's a reflection around psi. So this angle between G phi and psi should be equal to the angle between phi and OF phi. And so this angle is x plus gamma, and subtract this theta over 2. And then this angle here is gamma plus theta over 2. And then the easy equation you solve, you see x is theta. Okay. Yeah. So basically we go over algorithm. Okay. So this is a high level. Okay. Then we see the number of iteration in more detail. Okay, 5 minutes, so we can probably finish this part. Okay. So now we actually show why this is true and this is true in more detail. So number of iteration. Okay. And what's the theta we have there? So theta, I guess it goes here. Okay. From here, we can actually just calculate theta, because you think about what is this height here. So this height here is sine theta over 2. And this is the inner product with the two vectors we know. This is the inner product between phi and beta, right? Because sine theta over 2 is cosine of this angle. Okay. And yeah, so this projection of your psi on beta is sine theta over 2, and it's this one and it's this one. Yeah. So this is the geometry we really need to see. Okay. So sine theta over 2 is the inner product between beta and phi. I guess if you really want, you can get the absolute value, but everything has a plus coefficient, so it doesn't matter. Okay, and the inner product you can calculate easily to see that it is a square root n over n. Okay, and yeah, and this we already told you theta is about twice of square root n over n, but we do this a bit more carefully. So if theta is small, or n is much bigger than m, then you can do approximation of this just theta over 2. By doing it a little bit more carefully, so we say theta over 2 is greater than sin theta over 2, because our theta is something between 0 to pi over 2, and we have the geometrical thing, or you can show calculus that x is bigger than sin x in this range. Actually, x is bigger than sin x for every positive x, but anyway. Yeah, x is bigger than sin x, and so theta over 2 is bigger than sin theta over 2. Okay, and so you move things around, then you see 1 over theta is less or equal to 1 over 2 square root n over n. Okay, and yeah, yeah, 1 over theta is less than or equal to 1 over 2 square root n over n. And we say now we see how many rotation we want to say we do big R rotation, and we know after big R rotation and the result we end up at big R plus 1/2 theta, and we want it to be the closest to beta we get. Okay, and so this thing, so we think about we might overshoot. Okay, but we don't want to overshoot more than 1 over 2 theta. Okay, so this is about 1 over 2 pi over 2. But then we say we might have some error because it is not exactly pi over 2. But the overshoot we have should be less than 1 over 2 theta. Because if we overshoot more than 1 over 2 theta, we can just go back and we get a better approximation. Okay, so we are either here, and this error should be less than 1 over 2 theta. And then, okay. And so big is possible, all we need is satisfy this equation, and then we just move things around, and yeah. So you divide this around, and 1 over 2 cancel with 1 over 2, so you see that r is less than or equal to pi over 2 theta, and we have 1 over theta less than or equal to this thing, and so r is less than or equal to pi over 4 and the square root n over n. Okay. So this is our n over n part, and we have more coefficient here. And I think with a careful proof, you can prove that pi over 4 is actually tight. Okay. But anyway, here we have this, but for now we only care about order, then it's order n over n square root as we want. Okay. And yeah, I think it's a good time to stop here. So this is what we do, and then next time we'll go into a little more detail about this algorithm. Okay. So something about what's a small error probability here. Oh, that's probably next time. But yeah, so there are details to deal with on this algorithm. There might be some small error probability you want to get rid of, and also then there's a problem of what if you don't know m, etc. Okay. But yeah, so that we'll deal with next Tuesday, and yeah, so see you next Tuesday, and we'll have some homework on, I think, a little more on quantum Fourier transform, and also homework on having Q-skit, playing with Q-skit. Oh, more like quantum IBM quantum composer, but yeah. Okay, so see you next Tuesday.